Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. If you step on inside, we are going to look at the Chapter 4 review of the Big Ideas Math Integrated Math 2 textbook. A lot of things on solving quadratic equations using methods other than factoring, or perhaps using factoring as needed. But graphing, square roots, quadratic formula, completing the square, and perhaps with imaginaries, and solving nonlinear systems, and simplifying complex and imaginary numbers. Trying to think if there's anything else along the way of that. I think that's simplifying radicals. That's actually where we begin, simplifying radicals. So at the time of this recording, I haven't yet covered I haven't made a video yet on 4.9. Who knows, maybe at the time that you watch this video, I've done the 4.9 one, but you know, maybe I get to talk about that one a little bit more deeply. Oh, and that's the other thing, graphing inequalities, quadratic inequalities, and solving those. So we're going to go ahead and do some of that. I haven't really looked at those problems yet. We'll take a look. There are 57 problems of these to do. However, because it's a review, and because they have some examples before leading into the problems as close to the actual problems as they are or not, I am uncertain. But as much of that is, you know, more of me doing, less of me teaching, unless I want to find other ways to do the problem or something like that. But check the description section down below for the PDF of this actual assignment. Get yourself your own sheet of binder paper, or print out also the graph paper that I'm going to provide for you in the PDF, and find the timestamps to the kinds of problems that you're going to want to try and find. Watch some football on the back of Bengals Jaguars, I believe. And let's go ahead and get into the action, shall we? We are going to start with section 4.1 on simplifying or properties of radicals, and we work on simplifying radicals. What you see on this part A problem, these are examples, simplifying the cube root of 27x to the 10th power, what you're doing is you take the square root of the product equals the product of these square roots. You can split them up as their own cube roots, if you will. And what you do is you take the cube root of 27, which is 3, just straight up, that one's the 3. The x's, notice how x to the 10th split up into x to the 9th times x. Not a required way of you writing it, but it's a good way of thinking about it. Basically, you divide the 10 by 3. You're not taking cube root of 10, you're taking cube root of x to the 10th. You're saying how many perfect cubes of x exist inside of x exist inside of or of x cubed exists inside of this radical. And there are 3 perfect cubes of them, because you have 9 powers of x that are inside there that can divide by 3 to get 3, and there's 1 that remains inside. Just like numbers can, you can have numbers that remain inside the radical. There's an x to the first power that remains inside after, as you work that out. So 3x cubed comes outside, cube root of x stays inside. In the next simplification, you are trying to basically you're trying to rationalize the denominator. There's an irrational number inside of it. You may be simplifying radicals along the way, but your goal is to get rid of that. And that is by multiplying both top and bottom of this fraction by the conjugate of the denominator. A plus root b has a conjugate of a minus root b. And when they multiply, you end up with the difference of 2 squares that cancels your radicals outright, leaves you with a rational value. 3 squared minus root 5 squared. 9 minus 5 gives you 4. And on the top, you distribute 12 into the 3 and the negative root 5 to get this 36 minus 12 root 5 all over 4. 36 and 12 can both divide by 4, and the 4 goes away. You get 9 minus 3 root 5. So we're probably going to be able to do some examples for ourselves with rationalizing the denominator. Let's go ahead and take a look at what we got. Starting with number 1, or numbers 1 through 3, where it looks like we're doing a more simplifying with regard to the variables and such, simplifying the radicals. So I'm going to begin with kind of that process. Once again, we're taking the square root of both 72 and the square root of p to the 7th. Treat them very separately here. Square root of 72, we've done a bunch of this. I'm going to kind of let this happen. Square root of 36 times square root of 2, which is 6 root 2. I got a 6 root 2 happening there. And p to the 7th is basically this. I'll write it this one time and then kind of see where we go from there. In which case, I'll probably do this for you. Root p to the 6th times root p. To the first, if that makes sense. And then square root of 36, like I said, is that 6. And then square root of p to the 6th is p cubed. You divide the 6 by 2, and then you have the square root of p here. 6 times p cubed goes out in front, 6p cubed, and root 2p you place all in one single radical. That's the final result of number 1. Number 2, we have, I got to move this thing over. Number 2, root 45 over root 7y. Now, this is unsimplified in 2 ways. Let's begin with the top, or at least the concept of what we have on this thing. You take the square root of both top and bottom kind of in their own separate way, like so. You multiply top and bottom by that. Boom. Okay? Now, root 45 in and of itself can simplify. Root 9 times root 5 gives you 3 root 5. That's what exists like that. This root 7y cannot simplify in and of itself, but the fraction needs to simplify by rationalizing the denominator. This one does not require multiplying by a conjugate. Just root 7y is its own term, so you may multiply top and bottom by root 7y in and of itself, and you will be squaring root 7y to get 7y. Let me write it in its own color so you know specifically that I was adding that in. So this becomes 3 root 5 on top. 3 root 5 multiplies with root 7y, and you get root 35y. So those guys multiply together like so. That's all inside the square root. And then root 7y times root 7y is 7y. Now you ask yourself 2 questions here on out. Can you simplify this radical anymore? Basically, are there perfect square factors that exist? No. Can you reduce this fraction at all, especially after having simplified? No. And notice what I'm talking about. I'm talking about the 3 and the 7 and something with y. No. You don't work these ones out. This is an irrational number. That is not, you don't cancel out the y's or anything like that. You're actually done. This is the final answer. It didn't maybe clean up as much as you wanted it to. It doesn't look perfect. The fraction's still there and such. And furthermore, I want to emphasize the point, guys. Your number is an irrational value. Unless they gave you perfect squares to begin with, it's an irrational value. I mean, there's nothing I can do about that. So that is the final result on that one. All right, number 3. You have the cube root of 125 x to the 11th all over 4. Well, over 4. So once again, it's that cube root of top and bottom mentality here. Even more so, we take the cube root of 125 and cube root of x to the 11th kind of in their own separate ways, and cube root of 4 down here. Now, 125 is a perfect cube. That number is 5. X to the 11th is not a perfect cube. X to the 12th would have been. X to the 8th, x to the 9th is, excuse me. So, once again, in that kind of, that's cube root down there. Give me one moment. You are splitting up. Once again, 11 divided by 3. 3 goes into 11 3 times. So there's an x cubed that can pull out of there. There's a remainder of 2 that could not come out of that thing. So it's going to look like that. That's how I'm going to write that. So I did simplify the top as much as I could. But the bottom, the cube root of 4 is not 2. It's not the square root of 4. It's not the same thing. But we have to multiply it by something on top and bottom here. Unlike the previous problem where we worked on rationalizing the denominator by multiplying by the identical thing. The reason why the identical thing works in that case is because multiplying a square root of something times a square root of something leads you to that square root of something squared. Well, here I would have to multiply either by 2 factors of 4 to get, say, cube root of 64 to get my 4 out, or I can multiply by an even smaller value if I'm able to come up with what it is, so I can find the smallest perfect cube possible. I think it makes it cleaner and easier if you do that. In this case, I'm going to do exactly that. The cube root of 8 is 2. So I can multiply top and bottom by cube root of 2 and cube root of 2. The reason I choose the number 2 is because 4 times 2 is 8. If I get the cube root of 8, I give myself a perfect cube, and I'm going to do exactly that. I want to get it as small as possible so I don't have to factor anything out that's unneeded later, simplify anything later. So 5x cubed times the cube root of, this becomes 2x squared inside of there. Down here, cube root of 4 times cube root of 2 is cube root of 8. That's cube root of 8. And the cube root of 8 is 2. And once again, we go back to the question of, is 5 over 2, can I reduce that? No, and these 2's don't reduce because that's not a 2 on top, it's the cube root of 2. And that is your final result on number 3. Okay, we're going to go to number 4 where we work on rationalizing the denominator, and if there's anything to simplify, we still will. We have 8 over root 6 plus 2. I'm going to multiply top and bottom by the conjugate of this. The way to clear out irrationals in the denominator this time, the only way is by multiplying by root 6 minus 2 times root 6 minus 2. I guess the only other way is negative root 6 plus 2 and negative root 6 plus 2. I just mean you have to multiply by a conjugate. you have to multiply both sides, top and bottom by a conjugate, and that's going to be this guy here. So on the bottom, not the more important part, but the reason why we chose this value is where I'm going to begin. We are going to be doing root 6 squared minus 2 squared. That's the difference of two squares. A plus b times a minus b is a squared minus b squared. And then the 8 distributes into root 6 and 2, and you get 8 root 6 minus 16. Honestly, I'm probably going to rewrite this so that the... I don't want to speak too soon. I was going to say I want the irrational value second, but, I'll deal with it as it is. 8 root 6 minus 16 on top. I'm not going to do anything with that until I clean up the bottom. I got root 6 squared, which is 6, and then minus 2 squared, which is 4. 6 minus 4 is 2. So all of these can divide by 2, or each of these can, and you'll get 4 root 6 minus 8. Again, the root 6 does not divide, and it wouldn't as long as you're dealing with a factor in that term that did divide by 2. Once one part divides, the other part does not have to. That's the final answer. Okay, let's go to number 5. Now, number 5 is of a different breed, no fraction. However, you are trying to, I don't know how to say this, combine like terms, but you can't combine these as long as there's no common factor that exists in both of these. But if you could simplify one of the radicals, like that root 12 is also root 4 times root 3, or 2 root 3. And what you end up having, 5 times 2 is 10, what you end up having here are now like terms after having simplified the radical. There's a benefit to doing that. This is among them. Now you kind of combine like terms. It's like 4x plus 10x, It's 14x, 14 root 3. There's a simplified version of that answer. And I think even you'd agree that that is a better looking version. One term, all cleaned up, good to go. Number 6. Same kind of problem, but with cube roots and a subtraction. Number 6, 15 times the cube root of 2. What's sad is these are the fast problems to do. Later we got to do a lot more when we got to do solving methods and graphing. I see graphing coming right below. Minus 2 times cube root of 54. So same kind of thing. Cube root of 54 can break down more. Let's see what that will become. See, the review can only ask you so many different kinds of questions, so they really evolve fast in the kinds of questions that they do ask. 27 is a perfect cube that factors out of 54. Cube root of 27 is 3. Now, 27 times 2 gives you that 54, so cube root of 27 times cube root of 2, or 3 times the cube root of 2 is there. And so you can see they're both cube root of 2s. That's going to work out when we multiply that. 2 times 3 is 6, so 6 times cube root of 2. 15 minus 6 is 9. So as you have those like terms combined, you get 9 times the cube root of 2. And that's your final result. Number 7, we have 3 root 7 plus 5 quantity squared. And I'm going to work this out as if you know how to square a binomial without foiling, without expanding. No, you don't do this squared plus this squared. No, no, no. Now, those do happen. We will be squaring 3 root 7. We'll even be squaring 5, but there's a middle term. It's a squared plus 2ab plus b squared. There's a 2ab. Boom. 2 times 3 root 7 times 5 is in the middle. 3 root 7 squared, you do square the 3 and the root 7 this time. In a product, you square every portion of it. 9 times 7 is happening there. Plus, now 2 times 3 times 5 is 30, so that's 30 root 7, and then plus 25. 9 times 7 being 63. I'm going to put the 25 in front because that's the end thing that's going to add with it, right? 63 plus 25 is 88. So you get 88 plus 30 root 7. And that's what happens when you square that. And then number 8, last part of section 4.1. Approximately 1/7 of everything we're going to do here. Number 8, we have root 6 times root 18 plus root 8. If memory serves, and just me having done these problems a lot, probably will, it's better to simplify what's inside first beforehand. If for anything else then, which happened a lot in the book, this is where, if memory serves, you might be able to combine these two into a single monomial before anything else. And you got to simplify later anyway. So don't distribute immediately if there's something to simplify, and there totally is. Root 18 is root 9 times root 2. That's 3 root 2. Root 8 is root 2 times root 4 times root 2, which is 2 root 2. And 3 root 2 plus 2 root 2 can become 5 root 2. So you can multiply root 6 by 5 root 2. Root 6 multiplies by the root 2 to get root 12, and that's 5 root 12. What I like about this problem is there's still something to simplify after this. You're not done. Square root of 12 is root 4 times root 3, or 2 root 3. And 5 times 2 is 10. So you get 10 root 3. And I think we can once again agree that this is cleaner than what we had before. And there's more than one way to do it. You can distribute first, but now I'm dealing with root 108 and root 48, and simply just bigger numbers. When you don't have to deal with bigger numbers or multiply more things, it saves you time. And probably better chance of getting it right if you do what I did there. Okay, we are going to go to numbers 9 through 13 in a moment, but before we do, let's take a look at what they want to give us for examples for section 4.2 in solving by graphing. Now, we're going to use some solving systems using graphing in section 4.8 later, and one of these methods really is almost very similar to what we have. Darn near identical when all's down to it. I don't know if they show it here. I'll mention it and see if it's worth showing. We're going to solve x squared plus 3x equals 4 by graphing, and they say to write it in standard form. Basically, get everything on one side of the equation set equal to 0. That way, you can take this expression and graph this as if it's y equals this. They show you that much right here. Y equals x squared plus 3x minus 4. Because what you're doing is you're comparing y equals x squared plus 3x minus 4 to y equals 0. And y equals 0 is the x-axis. You're trying to figure out what the x-intercepts of this graph are. Wherever they cross are the values of x that will give you 0 for y. So you graph it. You find your means of graphing it, right? They don't tell you how to. The idea that we put in place is we can use negative b over 2a for the x value of the vertex, plug that in to get the y value of the vertex. I use this concept of 1, 1, 2, 4, 3, 9. They probably use a table or a graphing calculator. We'll see what we end up doing. I'm probably going to use my method. I just hope that, let me grab a graph. I hope that it's to scale, that I can, not to scale. I hope it can fit within a scale like this from negative 10 to 10. We'll see if it doesn't, and I will exclaim that immediately, and I'll change it if it doesn't. But the x-intercepts here were negative 4 and positive 1, and those are the values of x that we solve for. The method number 2 they could have chosen was graph y equals, that doesn't work, was graph y equals this equation. Basically, treat them as they are right now. Y equals x squared plus 3x, graph it. Y equals 4, graph it. For the sake of this problem, I probably would have done that personally, because this is an odd linear coefficient, negative b over 2a, whereas I could have factored out x. I probably would have preferred this method in some, right, actually it would have given me the same issue. But, point being, you have different methods. Where would those intersect? At what x values is basically the question. Okay, let's deal with number 9. Now, number 9, we are going to be solving x squared minus 9x plus 18 equals 0. Now, if you know how to factor this, I already see in my head what the answers are going to be. You could solve by factoring, but of course they're forcing the graphing on you, right? So we are going to be graphing this, but in order to do so, let's find the means to graph it. I'll be using that negative b over 2a approach personally, at least for this problem. I'll use a completing the square version, probably on number 10. I'll probably even use the second method on number 10 and talk about both of them. So this one is really that method number 1 where you graph y equals this. Well, y equals x squared minus 9x plus 18. And I'm going to go about this whole, the vertex is at x equals negative b over 2a, which is 9 over 2. Also 4.5. So I know that the axis of symmetry on y equals 4.5. Looking a little bit, x equals 4.5, excuse me. Looking a little bit like this. The y value of the vertex, you substitute 9 over 2 into this thing. 9 halves squared minus 9 times 9 halves plus 18, which gives you 81 over 4 minus 81 over 2 plus 18. 18 is, sorry, I'm doing this in my head. 81 over 4 minus 81 over 2 is negative 81 over 4. 18, I can multiply top and bottom by 4 over 4, and I get 72 over 4. Negative 81 over 4 plus 72 over 4 is negative 9/4. Yeah, negative 9/4. So your vertex is at 9/2 and negative 9/4. Now, negative 9/4 is negative 2 1/4, negative 2.25. So I'm going to plot that right there. And from here, I'm going to get some points out using my stretch factor of 1. I got 1, 1, 2, 4. Only if you've been graphing with me since chapter 3 do you maybe understand what I'm talking about. If not, I apologize. 3, use the table. 3, 9. That's all I'm really going to fit, and I'm going to rough this thing through and kind of show you what this is hitting. And look, you can plug in points for this as well, because I'm only, and look, there's a y-intercept of 18 that I can't fit. I'm only plotting, I'm not plotting points on integers, so I'm only roughing in my guess as to where it's actually going to be hitting. But of course, I also know where it's going to hit if you solved it by factoring. Where is it crossing the x-axis is the question. Boom there. Use purple. Boom here and boom here. Where are we crossing the x-axis? What are those x-intercepts? X equals 3 and x equals 6. Those are the two values of x that give me 0 when I substitute them into here. If you factor this, you do factor it to x minus 6 times x minus 3. That is number 9. Now, that was a single problem. Like I said, numbers 1 through 8 went a lot faster than just that one problem there. Number 10. Let's do it again, right? And that fit within there. So I trust all of these will. That's not a guarantee. I just trust them. X squared minus 2x equals negative 4. So you have two options. Let me kind of show you them both. Let's go to what we just did before using method number 1. Method number 1 will basically be set this equal to 0. So we'll have x squared minus 2x plus 4 equals 0. We're going to graph y equals this. We're going to graph this guy as if it's y equals that. So we're going to get a vertex of, you know what I'm going to do? I'm going to take graph y equals x squared minus 2x plus 4. I'm going to go ahead and take that equation, and I'm going to do this by completing the square this time. I'm going to get the vertex form out. So y equals x squared minus 2x plus blank plus 4 minus blank. X squared minus 2x plus 1. You divide negative 2 by 2 and square it. I'm trying to think. Admittedly, at the time, you might not have known completing the square yet in section 4.2. But now that we're there, I'm using it. And this factors to x minus 1 quantity squared. And 4 minus 1 is 3. So my vertex form is this, which then would reveal to me my vertex itself, which would be at 1, 3. So if your vertex is at 1, 3, we're trying to figure out what x-intercepts this thing has when we go over 1 up 1, over 2 up 4, 2, 3, 4. And I didn't fit over 3 up 9, but really, we're trying to find out what x-intercepts it has. Where does this thing cross the x-axis? Because remember, we're comparing this to y equals 0, right? Y equals 0 is right down here. These things don't intersect together. So if they don't intersect together, then there is no real, or there are no real solutions. They don't cross the x-axis. But that's method number 1. Method number 2 won't get you a different answer. I hope you understand that. I'm just saying there's a different way of going about this. For method number 2, is graph them as they are. Meaning the original equation looks like this. X squared minus 2x equals negative 4, right? I want to graph y equals x squared minus 2x. I want to graph y equals negative 4. Now what I did in the past was I called them f of x and g of x, just so we can really differentiate them. X squared minus 2x and g of x equals negative 4. Just graph them as is, just like that. Find out where they cross each other on x. Now they won't end up crossing each other. We kind of saw that. But at least this lets me talk about different methods of graphing and something that actually has more to do with section 4.8 later, solving these, because this is exactly what we do on 4.8. We graph two y equals equations and we find where they intersect. The difference with 4.2 is I only care about the x values. In the systems in 4.8, I also care about the y values, but whatever. So g equals negative 4 is straight up just this right here. Boom, there's that guy. I think a little darker green than I wanted. It's a little lighter green than I wanted. That might be the right green. That might have been the green. X, the blue one right here, this factors an x out of here, and you get x minus 2. You have x-intercepts. Remember, you're not looking for x-intercepts anymore as far as your answer goes, but my x-intercepts I'm going to use to graph. 0 and 2 are the x-intercepts. If you know enough about stretch factors, you would know we're going to hit this as your vertex. But furthermore, your vertex is directly in between your axis of symmetry is directly in between your x-intercepts because they're two values of the same height. But what is the y value? For x equals 1, f of 1 is 1 squared minus 2 times 1. 1 minus 2 is negative 1. So your vertex is at 1, negative 1 right there. And then you go 1, 1, 2, 4, 3, 9, etc. Now, I wasn't prevented from using negative b over 2a to graph or anything like that. I'm just showing you all different methods, just like I showed completing the square and now intercept or factored form to be able to do this same thing. But what we notice is the same thing here. Despite the fact that these have x-intercepts, that's not what I care about. What I care about is where do these two graphs intersect? The answer is they don't. They do not intersect. So once again, going back to the whole what's your solution set, there are no real solutions. No real solutions. And that is number 10. One way or the other. Number 11. I could apply the same thing to number 11. Hold on. Okay. I could apply the methods 1 and 2 to number 11, and I'm kind of interested in doing it, but my graph will be out of window range if I do. So I'm going to steal the bigger graph for this. I will do both methods as I just did before, but I'm going to use this big guy here and then kind of demonstrate both of them for you. Method number 1, method number 2, all right? But number 11, we do have negative 8x minus 16 equals x squared. Method number 1 would recommend, and I don't think I need the huge graph for this on method number 1. For method number 2, I would. Method number 1 is once again setting these things equal to 0. So I'm adding the 8x and the 16 over. I want to make everything positive if possible. I'm big on the completing the square thing whenever I have an even linear coefficient, and we're going to run into those again. So I'm just going to do that. You can use negative b over 2a as much as you like to, but right here I'm going to go ahead and do that. Now, actually, no, you know what? I'm going to go. No, I'm not. This is a perfect square trinomial. I'm sorry. I'm just going to go straight into that. This is y equals x squared plus 8x plus 16. 16 is the square of half of 8. So this factors down to x plus 4 quantity squared. Call it intercept form, factored form, vertex form, what have you. Your vertex here is at negative 4 comma 0. We're at negative 4 comma 0, and that also means vertex on here, that's your only x-intercept. To further confirm that, stretch factor of 1, we got 1, 1, 2, 4, 3, 9. And by the way, the y-intercept here is 16. We'll confirm that right now. 4, 16, boom, hit the y-intercept right there. We are crossing only once this time on the x-axis. This is at x equals negative 4. This is the only answer, the only solution to this quadratic. And we showed it by graphing and showing across there. That's how you can have one solution. If when set equal to 0, your vertex is your only solution. X equals negative 4. That's using method number 1. Method number 2, we're going to graph them as they are. I'm going to graph f of x equals, I'll call the first one x squared. The second one I'm going to do the negative 8x minus 16. So g of x equals negative 8x minus 16. And I'll give you a different graph for these ones as well. I don't need any more information on on how to graph these, right? Y equals x squared is as kind of straight up as you can get with regard to its look. You're starting at the origin, and you got your 1, 1, 2, 4, 3, 9 biz. 1, 1, 2, 4, 3, 9, 4, 16. Now I'm going to plot as many points as I can fit. And this one will require an exercise of knowledge that I guess you just have to understand. You just got to believe. You really want to draw this as best as you can for a problem like this. Negative 8x minus 16, y equals mx plus b form. Your y-intercept is negative 16, way down here. We're going to have a slope of negative 8. That's down 8, right 1, and also up 8, left 1. Up 8, left 1, up 8, left 1, up 8, left 1. Now here's the problem with my graph. It doesn't actually, they don't intersect right there. So I got to kind of move this over as best as I can. Up 8, left 1. Notice that space right there? I'm going to hit that, but it doesn't hit the blue. Up 8, left 1, it hits the blue finally. So this is the part where it's like you really got to be careful about your appearance of your graph here. This is why method number 2 can also falter. So it's not about vertex hitting the origin, nothing like that. It's about where do these guys cross. But this is the first time we get to see something like this. So stretching this out, there's only one time the line intersects with the curve. And I'm going to speak more about that as that thing goes up. But this thing intersects right there. The question is, what is the x value? Not what is the ordered pair. It's negative 4 comma 16. But what is the x value? The x value is negative 4, just like that was negative 4. Now, this only does touch once. You might be wondering how it didn't touch before and such. Remember, these lines are very thick. We're not very zoomed in. But the other question is, does it hit later? The answer is no. This curve, this parabola, will start sharpening itself up more and more and separating like that, if that makes sense. Green goes there, blue goes there. This is a parabola. It does not have a constant rate of change. It keeps climbing. So they touch tangentially. It's like this. They touch tangentially at one point, and then they separate. Not like a big curve, and it's really hard to see that from there, but that is what they are doing. So method number 2 prevails, probably not as cleanly as you would have hoped, but it does. Okay, number 12. The graph of f of x equals x squared plus 7x plus 10 is shown. Find the zeros of f. Okay, just write f of x equals x squared plus 7x plus 10. Now this also factors, but they're showing you it right here. I'm just going to go ahead and highlight them. Find the zeros. You're finding where they cross the x-axis. There and there. That's it. I'm not going to draw anything on this. Just the x-intercepts are the zeros. So, here, I'll write this. This is when x squared plus 7x plus 10 equals 0. And going by the graph, seeing the graph, we get x equals, looks like negative 5, and x equals negative 2. And I think you guys can agree that those would be them, because this factors to x plus 5 times x plus 2. All right, there was a fast one. It's already graphed, that's why. Number 13, graph f of x equals x squared plus 2x minus 5. Approximate the zeros of f to the nearest tenth. Once again, completing the square looks like it's going to have its way with me when it comes to getting the graph out so I can get vertex form. I'm going to go ahead and x squared plus 2x plus 1 minus 5 minus 1. I will add and subtract, minus 1. I will add and subtract the same value, the number that I used to complete the square. Divide 2 by 2 and square it. This factors to x plus 1 quantity squared. And negative 5 minus 1 is negative 6, where I can now sketch this graph. I'm going to use the smaller graphing portion size here. We're going to approximate the zeros. They actually want you to use a calculator here. Even when they say graph, I bet they're even fine with you using a graphing calculator. I do not remember if they let me kind of use the zeros feature on the calculator. I assume I can. The vertex is at negative 1, negative 6. This does not hit integers. It has irrational but real solutions. Once again, stretch factor is 1. They're not having too much fun with it being anything else, which is fine. 3, 9, over 3 up 9, and over 4 up 16. I can actually fit that to the top at 10 like that. So there's a full graph. However, where are they crossing the x-axis? I do wonder. You can't just assume it's like at a half mark. It's definitely not. These are irrational, because that's not factorable. The top part's not factorable. Now, I am going to go to the graphing calculator for this. X squared plus 2x minus 5, or the one that I grabbed, the vertex form that I wrote. But y equals x squared plus 2x minus 5. And let's just go ahead and look at this graph. See the same thing that I basically have out, right? Look at that graph. We're going to find the zeros. I'm going to hit the calc above here, trace. You might have a different calculator than I do. The zeros, the left bound. Let's do the right one first. Left bound, right bound. Let's get to the right of it. and find the tweener, we're going to get 1.44949897. To the nearest tenth is just 1.4. So I'm going to write this on this page. It's okay that you don't see it. I'm just going to circle this. So x is about 1.4, and that does make sense with my graph. You'll see it in a bit. Let's find the other one. Left bound, let's get to the left. Let's get around -5. The right bound, 0. That's fine. Let's find the tweener. -3.4. So x is -3.4 about. Okay, so here's what I got for the two answers right here for this and this. 1.4 seems legit. -3.4 seems legit. It makes sense to me. I am done with that problem, and I think with that section of 4.2. So we won't have to look at graphing again, I believe, until 4.8 and 4.9. Whoops, I still want this page. I don't want this page, though. Let's go. All right. Section 4.3 is solving using square roots. You likely won't have an x term unless it's inside of a squared quantity, but then it won't be with an x squared term. Now they have an example solving a sprinkler. It's a word problem. A sprinkler sprays water that covers a circular region of 90 pi square feet. So that's the area. Areas pi are squared for a circle. Find the diameter of the circle, which is twice a radius. So they give you areas pi are squared. The area is 90 pi. If you divide both sides by pi, you're left with 90 equals r squared, and they solve using square roots. Now, they didn't write, or the book doesn't seem to have this printed out in the E version, but there's this plus or minus aspect. Plus or minus root 90, plus or minus 3 root 10. Root 90 is root 9 times root 10, where you get 3 root 10. So the radius is either positive or negative 3 root 10, but a radius, a length, distance cannot be negative. So they're going to remove the negative versions from these. We'll outright ignore them. So only 3 root 10 is being considered for radius. Now radius is half of a circle's diameter, so they double that radius, right? 3 root 10 doubled is 6 root 10. So 6 root 10 feet, or it looks like approximately 19 feet. That's the diameter of a circle. With it, what does this have to do with? A sprinkler sprays water. The region that the sprinkler's covering, there's a full diameter of about 19 feet that's being hit. And a diameter, guys, is this full length right here, whereas the radius is just that length right there. Okay, these aren't word problems in general, but it was solving using square roots. I didn't write that, but they kind of did. You take the square root of both sides right there once you get the squared term or quantity by itself. Squared variable or quantity by itself. So let's go to number 14, where we are solving x squared plus 5 equals 17. I do want to get x squared by itself, subtracting 5 from both sides. I want to take the square root of both sides, where I'll get x equals plus or minus. This will exist here. These are not word problems. We will have this. Two answers. Root 4 times root 3 is 2 root 3. These problems should go pretty fast, especially because I've taught this before. I think, yeah, I'll just let you go to the playlist to find other problems of the sort that we have. Number 15. X squared minus 14 equals negative 14. If I add 14 to both sides, we'll get 0 here. Well, x squared plus 0, but x squared and then 0 on this side. If you take the square root of both sides, what do you square to get 0? Well, 0. X equals 0. There's just one answer. It's one of those instances of like the vertex hitting the x-axis or something like that. One solution. Number 16. X plus 2 quantity squared equals 64. Instead of trying to expand this thing out, this is a benefit to you to have this squared thing. We're going to be doing this by completing the square in the next section. So you want to go straight from here and take the square root of both sides. The square root of x plus 2 squared is x plus 2, provided that the square root of, on this side you have the plus or minus, and the square root of 64 is 8. If I subtract 2 from both sides, I'll get x equals negative 2 plus or minus 8, and I want to actually compute those two things. What is negative 2 plus 8? What is negative 2 minus 8? Negative 2 plus 8 is 6. Or negative 2 minus 8 is negative 10. Two different answers. Which also means this was factorable if we wanted to find a way to solve this. So was number 15. Well, can't really factor 15 when you get 0 as a solution, but that's okay. Number 17. 4x squared plus 25 equals 75. Let's once again get the x squared by itself, but it takes 2 steps this time. You subtract 25 from both sides, which is a crucial step. Now, you could take the square root of both sides here. I do not recommend it. People forget to take the square root of 4 if that happens. Divide by 4 first, even though a fraction is a result of this. 50 over 4. Now, I could reduce this to 25 over 2. Not an overall bad gesture. However, because 4 is a perfect square and reducing this fraction would give it a non-perfect square, I'd rather deal with it where I'm at. It's not wrong to do the other, and you'll see a lot of people maybe do that. There's no problem with it. I just know that if rationalizing the denominator is something I'd have to do afterward, taking the square root now is great. And square root of 50 is on top. That's root 25 times root 2, or 5 root 2. And there's a plus or minus here. That's the final result. I didn't need more work than that. Number 18. X minus 1 quantity squared equals 0. Unlike number 15, when we're taking the square root of both sides here to get 0, sure, we get 0, but there's still another step to go because there is an x minus 1 on that side. We still have to solve for x afterward. There may be 0 on the right, but here I have x minus 1. I got to add 1 to both sides, and I get x equals 1. Once again, just a single answer, but it's not 0 this time. It is 1. And then number 19, I get 19 equals 30 minus 5x squared. I want to get 5x squared by itself, and I want to make it positive, honestly. I'm going to add 5x squared over. And then let's subtract the 19 on the other side to get 5x squared equals 11. Now we're going to divide both sides by 5. Same kind of thing as before. Don't take a square root until you get this thing by itself. You get 11/5. Unfortunately, not only can this not reduce, but 5 is not a perfect square. So when I take the square root of both sides, I'm going to have to do some rationalizing denominator biz. Unless you wanted to turn 5 into like a 25, but that's kind of what we're going to do here when it comes to the rationalizing denominator stuff. Plus or minus root 11 over root 5, yeah? I need to multiply top and bottom by the square root of 5. This will rationalize that denominator. See, this is where we kind of get that 25 out. Root 5 times root 5 is root 25, so on the bottom you will get that 5. Square root of 11 times square root of 5 is square root of 55. 55 has no perfect square factors in it. You are done. Plus or minus root 55 over 5. Finito caput. Okay, section 4.4. Section 4.4, we are going to be solving by completing the square. Now, completing the square gets you to basically this stage right here where you take the square root of both sides, that kind of stuff. You'll actually see it in the example that they give. Let's take a look. Solve x squared minus 6x plus 4 equals 11 by completing the square. Now, in these problems, it is much better off if you get a 1x squared. Excuse me. You got to get a 1x squared. For all intents and purposes, get a 1x squared. You're much better off if you have an even linear coefficient. I even said as much when we were talking about graphing in 4.2. But you need to find a constant that's going to give you a perfect square trinomial on the left side of the equation. 4 is not the number that works with these two terms. We got to find something else. So we subtract 4 from both sides, make it 7. Now they're going to find the value that gives you a perfect square trinomial. We take negative 6 and divide it by 2, your even linear coefficient, and then you square it. They show that same thing. Negative 6 divided by 2 squared. Negative 3 squared gives you 9. I'm going to write the 9 as that thing is. And so this is 9. Whatever you add to one side, you add to the other. And that's what they do. This factors to x minus 3 quantity squared, and 7 plus 9 is 16. Now you're at that stage where you solve using square roots, and that's exactly what they do. They take the square root of both sides, and they do their thing for solving. You get plus or minus 4, although it doesn't show. Plus or minus 4. And then you add 3 to both sides. X equals 3 plus or minus 4. 3 plus 4 being 7. 3 minus 4 being negative 1. Let's do more of the same, starting with number 20. Number 20, round solutions to nearest hundredth if necessary. I'm going to first write an exact answer before I do that, and you probably won't see me write stuff in the calculator for it, but I'm going to go for it. Okay, same thing as before. In fact, it's the same number in essence. It's a positive 6x instead of a negative 6x, but I'm going to complete the square here. Negative 40 wasn't cutting it, so I added it over. If I add something to one side, I got to add to the other side, just like this 40. This number is going to be a 9. We just saw that from the previous problem. 6 divided by 2 is 3, which actually ends up in the factorization. And 3 squared is 9. But the fact of the matter is I had to add 9 to both sides. 40 plus 9 is 49. We will take the square root of both sides, just like we were solving a second ago in section 4.3. We get x plus 3 equals plus or minus 7. and we subtract this 3 over. Negative 3 plus 7, negative 3 minus 7. Let's figure those out. Negative 3 plus 7 is 4. Negative 3 minus 7 is negative 10. These are the solutions, which means this was factorable, but they had us use this method. When we get to section 4.7, we can solve using any method that we choose, and if something's factorable, that's how I'm going to go about it. Actually, I'll give all the different versions. I think that's something you guys like to see, but I will do factoring as one of them. Number 21, x squared plus 2, x squared plus 2x plus 5 equals 4. Little lot more of the same. I'm going to subtract that 5 over because it is not the one that I'm looking for, basically. 4 minus 5 is negative 1, and let's find the one I am looking for. 2 divided by 2 is 1. 1 squared is 1. We've seen that actually a couple times now if you followed my graphing problems. This factors to x plus 1 quantity squared, and negative 1 plus 1 is 0. Hey, this looks like that was x minus 1, but this looks just like this problem. We're almost done. We're almost done. Take the square root of both sides. You get x plus 1 equals 0, square root of 0. Subtract 1 from both sides, and that's it. That's all. You can double check it. It shall work. Number 22. 2x squared minus 4x equals 10. Do not bother trying to complete the square as long as that 2 is there. We're lucky that we have all even numbers. It's pretty good because we can divide them by 2. Do it. Don't not. You will not get a perfect square trinomial if you don't. You might mess something up. So let's go ahead and complete the square. We've seen this several times now. This is a 1 and 5 plus 1. And this factors to x minus 1 quantity squared equals 6. Taking the square root of both sides, 6 is not a perfect square, so we will be doing some rounding after we are finished. That's x minus 1 is plus or minus root 6. Add 1 to both sides, x equals 1 plus or minus the square root of 6. That's one set of the answers. We go to the calculator and figure out what 1 plus root 6 is. Whoops, let's get out of that graph from before. 1 plus root 6 gives me 3.449. Wait, was this the equation from before? X squared minus 2x equals. Well, it was a plus. Okay, it was opposite signs. We had this before. So I'm gonna guess it's gonna be 3.45 and then negative 1.45. I'm saving the calculator bits and I'll just write it out. So x is about 3. They said nearest hundredth. So 3.45. and about negative 1.45. I don't know if it's just the same question writer that can't seem to do any completing the square other than a bunch of these ones with ones and just get these same answers out over and over. So, okay. All right, let's move forward and determine whether the quadratic has a maximum or minimum value and then find the value. Number 23. So on these problems, we're all about the vertex, if you will. A parabola can either go up or go down. We can determine that based off the a value. If the a value is negative, it goes down. Something that goes down is a maximum, and something that goes up has a minimum. It's at the vertex. Minimum meaning the lowest point and the highest point. This goes down forever, has no min. This goes up forever, has no max. But you can determine based off that. This one has a max. Where is it? We got to find the vertex's y value. In terms of HK, we got to find K. So given that we're in the completing the square section for this, I'm going to do that by completing the square. A lot of what I did in section 4.2 when I was able to. Didn't use a lot of negative b over 2a, but you have to first factor this negative out of here. I did mention you need a 1x squared in here, but the negative 1's not involved. It's not a part of that. I'm going to still complete the square inside here. We will get a 9. Divide negative 6 by 2 and square it. We'll also subtract 9 over here. However, the 9 over here will be multiplied by a negative 1, just like the negative 1 here multiplies by this 9. So we subtract the result of the negative. I know that might get confusing, but the whole idea is this isn't really a 9. It's really a negative 9. So we add negative 9 here. We subtract negative 9 there is the end goal. This factors to x minus 3 quantity squared, but the more important part is this k. This is negative 1 plus 9, right? This is basically just a big plus. Negative 1 plus 9 is 8. You get plus 8. So in vertex form, boom, this is what it looks like. But the maximum value or the minimum value is the y value of the vertex, which is this guy. your max value, the max itself, is 8. That's what we got. The vertex is at 3, 8. The max is 8. All right, number 24. Same thing. This one's arguably easier. Number 24 is an upright facing graph based on A being positive 1. And with A being positive 1, like I said, completing the square is going to be decidedly easier. So, listen, straight up, it'll have a min. It'll have a min. Let's go ahead and find that value that completes the square inside here. X squared plus 4x plus blank plus 11 minus blank. 4 divided by 2 is 2. 2 squared is 4. So that'll complete the square. We are now going to factor this guy down. The less important part, but it's x plus 2 quantity squared. And 11 minus 4, the more important part, is 7. Plus 7, that is your max, or your min value. Your min value is 7. Okay. Number 25. I have y equals 3x squared minus 24x plus 15. Now, the previous equation where I was able to divide everything by 2 on number 22, I cannot do the same thing here because on number 22, I didn't have a second variable like this y equals here. However, because I still need to get a 1x squared out, I'm going to do the same thing as I did on number 23. Factor the thing that's out of in front of x squared for the first two terms. The plus 15 I'm going to stick on the outside over here. That's uninvolved from this inside. I factor 3 out of there, and we're going to find another value that completes the square. And then we will subtract that here, keeping in mind that that number will be multiplied by 3, just like this number is multiplied by 3. Negative 8 divided by 2 is negative 4. Negative 4 squared is 16. This will also be a 16. So this factors into y equals 3 times x minus 4 quantity squared. And 15 minus, looks like 48, is negative 33. Oh, this, by the way, this thing has a minimum because the a value is positive. Negative 33 appears to be that minimum. That's as low as it goes. That's number 25. Number 26 is a word problem. The width of a credit card is 3 centimeters shorter than the length L. The area is 46.75 square centimeters. Find the perimeter. Okay, so credit card is a rectangle. Okay, so for this rectangle, we have some width, we have some length. Now, the width is 3 centimeters shorter than the length. Width is 3 centimeters shorter than length. But length times width, let me write it. Yeah, length times width is the area. So I'm going to write that as length times width, like that, is area. And now we have this whole setup that can be a quadratic. So let's bring that over here to make it L squared minus 3L equals 46.75. Now, there's a lot I don't like about this problem. However, by the nature of completing the square, I got to leave this as a 1. So I can't do this whole, what you'll see me sometimes doing quadratic formula, like multiply this by 4. I'm not going to do that because this needs to be a 1. So I'm going to have to deal with this, and we're going to go ahead and work it like this. Negative 3 divided by 2 is negative 3 over 2, and negative 3 over 2 squared is 9 over 4. Now, I'm going to rewrite that as a decimal because the other side's doing a decimal. 9 over 4 is 2.25. 2.25, and that's what's happening over here. Looks like this will clean up. 46.75 plus 2.25. This factors into L minus, 3 halves is the number that you multiply to itself to become this, add to itself to become this, and that's 1.5, and that's the factorization. I'm going to write these as decimals. And this is 49. 46.75 plus 2.25. That's good. Taking the square root of both sides means I can work off that. Square root of 49 is 7. Now, normally I'd write plus or minus 7. However, because you can't have negative length, I'm just going to deal with the 7 itself. Add 1.5 to both sides. L equals 8.5. Your length is 8.5 centimeters of your credit CAD. And I haven't researched that. I'm sure that's very close to accurate, if not exact. The width equals L minus 3. Width is 3 centimeters shorter than this length. Width is 5.5 centimeters. Did they ask for both? Find the perimeter. I'm not done. I was going to be done. The perimeter of this thing, there are 2 L's and 2 W's, 2 lengths and 2 widths. Area is the inside, perimeter is the outside all around. Perimeter is 2 lengths plus 2 widths, which is 2 times 8.5 plus 2 times 5.5. That's 17 plus 11, which is 28. 28 centimeters. Not square centimeters, it's still one-dimensional units, even though it went around two-dimensional track. 28 centimeters. Not halfway home even when it comes to number of problems attacked. So, I don't know. It still might take a little minute. Not yet an hour through, though, either. Okay, here we go. Section 4.5. Quadratic formula. X equals minus b plus or minus the square root of b squared minus 4ac all divided by 2a. So, in this problem here, solve negative 3x. I'm trying to fix all these plus or minuses here. Negative 3x squared plus x equals negative 8 using the quadratic formula. You'll see the first thing that they do is set it equal to 0, which is a must. Something that I would recommend that they didn't do was turn my a positive, because I don't like a negative denominator. It's actually kind of one of the simplification rules. You're not supposed to have it, since they ask you apparently, well, they don't, but, round to the nearest tenth. I guess they do later. They rounded these to the nearest tenth, so I guess they don't care that that's negative. I will. I'm going to have that positive. So anyway, they still set it equal to 0. You can't identify A, B, and C unless it's 0. A is negative 3, B is 1, C is 8. What I will also do, unlike what they had, which they do a lot of internal work here, is I'm going to evaluate the discriminant probably first, b squared minus 4ac. Looks like I'm going to have to do it for these problems later, finding the number of x-intercepts, but b squared minus 4ac will help me streamline this process a little bit more than normal. So, what do? They do negative b, which is negative 1, plus or minus the square root of 1 b squared, 1 squared minus 4, times a of negative 3 times c of 8, all divided by 2 times negative 3. Once again, 2 times negative 3 is negative 6. But the inside, they do 1 minus negative 96. 1 plus 96 is 97. 97 is not a perfect square, so you have negative 1 plus or minus root 97 all over negative 6. Using the calculator, they get approximations of negative 1.5 and positive 1.8. They say round to the nearest tenth if necessary. I'll tell you when it is or not. 27 does not look necessary because it looks factorable. As long as it's factorable, no rounding will be had. We'll just get exact answers. All right, on number 27, I have this set equal to 0. My A is 1, B is 2, C is negative 15. I begin with the discriminant portion first of b squared minus 4ac. This evaluates to 4 plus 60, which is 64. 64 being a perfect square, this is the thing that goes inside the square root, b squared minus 4ac. So when it comes to solving, we have x equals negative b, that's negative 2, plus or minus the square root of 64. Square root, 64 is 8. All divided by 2a. 2 times 1 is 2. So we're going to be doing negative 2 plus 8 over 2 and negative 2 minus 8 over 2. So negative 2 plus 8 is 6, and 6 over 2 is 3. Negative 2 minus 8 is negative 10. Negative 10 over 2 is negative 5. That appears to be what I'd get if I solved by factoring. So I agree, and I move forward. Number 28. 2x squared minus x plus 8 equals 16. Let's subtract the 16 over. We don't have our true c until this thing's set equal to 0. Same with the other letters. This is the only one that's affected. My a is positive. I'm happy with where I'm at on this. Let's go ahead and do quadratic formula. Let's start with the discriminant of b squared, negative 1, minus 4ac. This becomes 1. Minus a negative is plus. 4 times 2 is 8, times 8 is 64, which is 65. 65 is not a perfect square. So this time when we do this guy, we're going to have to go to the calculator at some point. X equals negative b. Opposite of negative 1 is positive 1. Plus or minus square root of 65, which cannot be simplified more to my knowledge, over 2 times 2, which is 4. 1 plus or minus root 65 over 4. Let me just go with the calculator without your need to see what I'm doing behind the curtains. Root 65 divided by 4. I'm getting 2.2. How many to the nearest tenth? Around 2.3. So x is around 2.3. And let's do the minus root 65 all over 4 minus negative 1.8-ish. I'm not going to write ish, just negative 1.8. But this is fine as well, right? This is exact. Those are approximate. Start with the exact first, even simplify it when you can, unless it's a big old word problem. Number 29. Negative 5x squared plus 10x equals 5. I think I know what this kind of answer will be as well. 29. Negative 5x squared plus 10x equals 5. I'm going to add the 5x squared over. I'm going to subtract the 10x over with that positive 5, just like this. And I'm going to divide everything by 5. It is much, much more worth it to be able to work these things out in that way. Now, we've seen a lot of these before, guys. This is a perfect square trinomial. It'll not only be rational, but there will be one solution. But we still got to use quadratic formula. Start with the discriminant. B squared minus 4ac. That gives you 4 minus 4, which is 0. You aren't adding or subtracting anything with that negative b. So you're just left with the negative b over 2a. X equals negative b. I'm right here. This opposite of negative 2 is 2. Plus or minus root 0, right? I don't even really need to write that. Over 2 times 1. So 2. That's 2 over 2, which is 1. Just one answer, as this would have factored to x minus 1 quantity squared. So x equals 1. Okay, numbers 30, 31, and 32. Find the number of x-intercepts of the graph of the function. Now, there's more than one way to do a problem like this if you have the visual sometimes, but they are expecting a quadratic formula basis, which in essence will be, use the discriminant. Y equals negative x squared plus 6x minus 9. Now, in this particular kind of problem, I am fine and firm with, the whole negative b over 2a thing. I don't know if it's required that you say set equal to 0 here, but what I wanted to point out when doing this is I'm not forced. I said negative b over 2a. I meant b squared minus 4ac. I'm fine with a being negative in a problem like this because I'm not dividing by the 2a. I'm good with just discriminant, b squared minus 4ac. I think this is a little more hectic, though. Now I have 3 negatives, but 3 negatives does mean subtraction. 36 minus 36 will give me 0. So a 0 discriminant means one x-intercept. There's one real solution. If there's one real solution, there's only one place it crosses the x-axis. We've seen that graph before. It's where a vertex crosses the x-axis. And that's exactly what this graph, y equals this, would have done. Number 31, we have y equals 2x squared plus 4x plus 8. I think in the same vein, setting this equal to 0 gives me one added benefit that ordinarily I wouldn't be able to divide everything by 2. At least that's probably ill-advised to give an appearance of that if there's still a y in the equation. But if we're finding x-intercepts, we're finding out when this equals 0 technically. So when I divide everything by 2, I've made everything I've made everything smaller. It helps, even if a little bit. Your discriminant will be b squared minus 4ac, which is 4 minus 16, which is negative 12. Negative square root, taking the square root of a negative, is no good, right? This is where you have no x-intercepts. You don't cross the x-axis. I'm not saying it's no good, but no good to find where it crossed the x-axis. 0 x-intercepts in a question like that. We're going to be dealing with imaginary numbers after section 4.5, after this question, so get used to doing something with that after the fact. Number 32, y equals negative 1/2 x squared plus 2x. Once again, we're setting this guy equal to 0, at least that's the way I want to play with it. There is no c value that I can notice here. However, I want to do a little bit more. I'm going to multiply everything by 2. Heck, let's do negative 2 times negative 2 just so you're like, oh, what did you do there if you're watching me on mute, times negative 2 to both. I want x squared minus 4x equals 0. Let's make it good looking. My discriminant will be b squared minus 4ac. C is still 0. Well, that won't matter because c is 0 anyway. That's 16. So 16 is that number. That means 2 x-intercepts because it's positive. You get a positive discriminant, you get 2 real solutions, or 2 x-intercepts. You get a 0 discriminant, you get 1 real one real solution, 1 x-intercept. Negative discriminant, 0 real solution, 0 x-intercepts. Okay. And that is the first things pre-imaginary numbers. Let's now dive into imaginary and complex numbers by dealing with I. Let's look at the notes that they kind of have here. Perform each operation, write answer in standard form. You can see that using things with I is very much kind of like combining like terms. If these were x's, you'd get the same kind of answer. The difference is I is not a variable, so we're not writing it in front. Its standard form has I at the end. It's an imaginary component that multiplies with your numbers, and we're going to write it in a plus bi form, a being a real number, b being an imaginary number. So we combine the same way we generally would do anything. Parentheses minus parentheses, we distribute the negative. Now they're going to write it differently. They're going to treat the i's together. But they do distribute the negative into the 2. That's why you see a minus 2 here. And the negative into the 7. That's why you see a minus 7 here. But 3 minus 7 gives me negative 4. And then you combine the i's. Negative 6i minus 2i is negative 8i. There's that answer. On part B, they do a straight distribution in multiplication, 5i times 4, 5i times 5i. Same thing happens as if they were x's. Instead of 20x plus 25x squared, it would be 20i plus 25i squared. However, I squared is equivalent to negative 1. That's right, an imaginary number times an imaginary number is a real number, and it changes its sign in a certain way there. But 20i will still be involved. 25i squared is negative 25, but we will front this standard form with it. Real number first, imaginary number second. The third one, we have 2 plus 5i times 1 minus 3i. FOIL takes place. We got 2 times 1, 2. 2 times negative 3i is negative 6i. 5i times 1 is 5i, and 5i times negative 3i is negative 15i squared. Now, negative 6i plus 5i combines to become negative I. 2 is just hanging right there, while negative 15i squared becomes positive 15, because I squared is negative 1. 2 plus 15 is 17. You're left with 17 minus I. So we are going to be performing operations of those things. I squared is negative 1. Be mindful of that. And standard form is A plus BI. But let's start with number 33, where they say find the values of x and y that satisfy the equation 36 minus yi equals 4x plus 3i. Basically, the concept is here are imaginary sets together, and here are real sets together. These, blue doesn't intermingle with green ever. So green is kind of its own thing. 36 equals 4x, like that. These are equivalent if these parts are equivalent. Divide by 4, you get x equals 9. That's the value of x that would make this thing true. The value of y that would make this thing true is I got this negative yi equals 3i. Divide the i's, right? You know, negative y equals 3. Divide by negative 1, you get y equals negative 3. You're just finding out the value that makes the component thing what it is, so then the end result is what you get out of this. Like, this ends up becoming all of 36 plus 3i when you plug in those x's and y's together, right? That's the complex number that we're talking about in the end. Not much to it. Moving on, number 34, 35, and 36. Excuse me. Quite a bit like what you just saw previously here. So we have negative 2 plus 3i plus 7 minus 6i. And I'm going to rewrite this without parentheses. The addition really is doing nothing to this. Adding a negative is subtraction, but I combine like terms. Negative 2 plus 7 is 5. Please write that one first. 3i minus 6i is negative 3i. Write that one second. There's your standard form answer of number 34. Number 35, we have 9 plus 3i minus negative 2 minus 7i. So we did see one in the example set, and we've done this stuff since, I think, section like 2.2, where we have been able to distribute this negative. And that's exactly what we're going to do here. Distributing this negative means signs inside this set will change. Unlike the last one that was addition, kept the signs as they are. Now this time signs will flip. Subtract -2 is +2. Subtract -7i is +7i. But from here, you do what you did last time. Combine like terms, real numbers. 9 + 2 is 11, and 3i plus 7i is 10i. Number 36. 5 plus 6i times -4 plus 7i. Let's FOIL and then simplify from there. 5 times -4 is -20. 5 times 7i is 35i. 6i times -4 is -24i. And 6i times 7i is 42i squared. You cannot forget that I squared, just like x's. People do it too often. We gotta build off of it at some point. We can't just keep doing the same thing. I'm not saying you guys are, but you guys might be. If my students are, and I say it all the time, then who knows. Okay, so -20 is still hanging out. I got 35i minus 24i to be 11i. That's positive 11i. And 42i squared is -42. Remember, it does become a real number, but you do change sign. I squared is -1. -20 minus 42 is -62. So we get -62 plus 11i, and we're good. And then we have number 37, where it says multiply 8 minus 2i by its complex conjugate. Now, we've referred to conjugates when we rationalize denominators, but we did them with irrational numbers. So 8 minus 2i has a conjugate of 8 plus 2i. It does the same thing that irrationals do when you multiply by its conjugate. It makes these real and rational. So 8 minus 2i times 8 plus 2i is equivalent in difference of two squares format to 8 squared minus 2i squared. A squared minus b squared. 8 squared is 64. 2i squared, squaring 2i gives you 4i squared. And 4i squared is -4. So subtracting -4 is +4, which is 68. And that's number 37. All right, section 4.7. This thing should be pretty meaty, not only in what they provide for you, but how I'm probably going to go about the problems. Because I want to yawn. There's more than one way that you can solve these problems. They're going to let us use a method that we choose. I'm going to use any method that seems feasible, even if it's all of them. Not graphing, but anything else. The other part about this is not just choosing methods. Look at this very example. You have i's in your answer. Now that we've dealt with i's, the I is the square root of -1. When you take the square root of a negative, you get an imaginary solution. And they're conjugates, right? Plus or minus. Don't forget those. So x squared minus 4. Oh, by the way, this section is not going to guarantee you're going to have i's in it. It's just that now it's opening up to the notion that you can. So you're going to expect it sometimes. X squared minus 14x plus 53 equals 0. They took the method right out of my mouth, where they solved by completing the square. I would do this too, as long as you got a 1x squared and even linear coefficient. They subtract the 53 over, divide -14 by 2 and square it to get 49. -53 plus 49. This factors to x minus 7 squared, but you get a -4. So when you take the square root of both sides, the square root of -4 becomes 2i instead of just 2. 2i. The square root of a negative is not a negative number. You will be adding or subtracting it, but it's not a negative number. Excuse me, rather, it's just an imaginary number. You can have negative, positive imaginaries, but it's an imaginary number. We're going to add 7 over, and you get x equals 7 plus or minus 2i. They do not combine. You have 7 plus 2i and 7 minus 2i. Option B, not option B, part B, problem B, we have this quadratic equation set equal to 0. They say it's not factorable. I'll believe them. Completing the square result in fractions. I believe them. Quadratic formula seems best. I believe them. Negative b plus or minus square root of b squared minus 4ac all over 2a. Here, your b squared minus 4ac gives you a -144. There may be no real solutions and no x-intercepts, but there are two imaginary solutions, and we'll take the square root of that negative. Square root of -144 is 12i. We'll be adding and subtracting 12i as we work this thing out. And then, excuse me, I'm just getting tired. And then they go to fraction reduction after that. 6, 12, and 18 can all divide by 6. 6 over 6 is 1. 12i over 6 is 2i. 18 over 6 is 3. You get 1 plus or minus 2i all over 3. Two different answers in conjugate, as complex conjugates. So that's parts A and B as examples. We have 6 more problems to do. Technically 9 if you consider those bottom 3, because they are pretty much the same. I just have to write one step before it, and I'm good to go. Number 38. I have negative x squared minus 100 equals 0. I can solve using any method I so prefer. I'm going to solve this using square roots, at least as the main. So if I solve, let's do different colors for every method I do. If I'm going to solve using square roots, I'd love to get x squared by itself. Let's add 100 to both sides, divide both sides by negative 1, and then let's take the square root of both sides there. X equals plus or minus. Square root of 100 is 10. But because it's square root of negative 100, it's 10i. Those are your answers. Solving using square roots is best to me. Because it's imaginary, that means it's not factorable, so I won't solve by factoring. Because there's only a squared variable here and not an x variable, I'm not going to solve by completing the square. However, I will give you the quadratic formula equivalent. Negative x squared minus 100 equals 0, but I'll still go about it my way. I'm not using negative 1x squared. I'm going to divide everything by negative 1 to get positive 1x squared, just like that. And now we're going to be working on quadratic formula with the discriminant of b squared minus 4ac. The b term, the b coefficient is 0. 0 squared minus 4ac. C is 100. That becomes 0 minus 400, or negative 400. Now, x equals negative b, that's negative 0, plus or minus the square root of negative 400 all over 2 times 1. Now, square root of 400 is 20, so this will be plus or minus 20i all over 2. So x is plus or minus 10i. So you see how much more work had to be done by solving the quadratic formula, and that was me keeping it brief. Meanwhile, but that's number 38. I apologize if I keep yawning, guys. Let me deal with it. Let me pause it. Okay, so I'm back. And I was thinking when I paused it, I said, let me take care of this. I'm like, what am I going to do? Nap? I tried to yawn it out more. Unfortunately, I think it's just going to make me yawn more. But I did refill my water, so I'm good there. Okay. We finished 38. We're on 30. Okay, I already circled 39. We're on 39. So number 39. We have 4x squared plus 53 equals negative 11. Once again, solving using square roots seems like a good plan here because I have no x terms, right? So I can do 4x squared equals negative 64, divide everything by 4, and you get negative 16, and take the square root of both sides. Assuming I'm not missing anything there, x is plus or minus. This is 4i. Square root of 16 is 4. Square root of negative 16 is negative 4. I want to use all blue there. I forgot. So let's turn those blue. Except the square root symbols. That's fine to be black. Let's go. Yeah, same thing as before. Just completing the square wouldn't make any sense here because no x term. You can't factor. Quadratic formula is possible. If I'm going to use the quadratic formula, though, instead I'm going to add the 11 over, set it equal to 0, and you get plus 64 equals 0. Very close to the last problem. Divide everything by 4 just the same. No reason not to do that much. So discriminant, we're going to get, once again, b squared, 0 squared minus 4ac, which gives me 0 minus 64, negative 64. So we will get, that's the discriminant. So x equals negative b, negative 0, plus or minus root. Negative 64 is 8i all over 2a. 2 times 1 is 2. That's plus or minus 4i. Still get the same answer. I'm probably skirting some steps around when I use quadratic formula there, but it still works. See, I'm very used to, what I see here as examples is really how I used to quadratic formula things. Like, sometimes I'd spend a long time inside there, and that looks familiar. This doesn't look like quadratic formula to me anymore the way that I write it, but it is. It's still it. I just leave all the x equals negative b stuff out of the way if I can. Number 40. X squared plus 16x minus 17 equals 0. X squared plus 16x minus 17 equals 0. This looks factorable. I believe this factors into, let's not blow this out of proportion. Let's use a different color. Let's say factoring, I believe this factors into x plus 17 times x minus 1. Using zero product property, x can either equal negative 17 or x equals 1. There's a method. I can't use square roots this time. However, I can use completing the square, which kind of finishes into square roots. So completing the square on this stage here up top, x squared plus 16x. Add the 17 over because in cometh another number that I'll add to both sides. Divide 16 by 2, you get 8, and 8 squared is 64, so we'll add 64 to both sides, and this factors to x plus 8 quantity squared. 17 plus 64 is 81. Now you take the square root of both sides, and you can see why factoring was faster. X plus 8 is plus or minus 9. Subtract 8 over x is negative 8 plus or minus 9, where you either get negative 8 plus 9, which is 1, or negative 8 minus 9, which is negative 17. The same two answers we got by solving by factoring. Not significantly more steps. A few more than twice the amount. I'm still going to use quadratic formula for this guy, and we have that top 1x squared plus 16x minus 17. Let's just write the a, b, and c. A is 1, B is 16, C is negative 17. As long as it's set equal to 0, we're all taken care of. So here we go. Discriminant is B squared minus 4AC. By the way, this is the way that I did, the order that I wrote these in is the preferred order I would have done to solve them. Quadratic formula is on the bottom of my list for here. 256 minus 68 is 100. I guess it's 186, but isn't that's not a perfect square. 188. What am I doing wrong here? 48. 100. Why am I doing? It's 188. That's not a perfect square. Oh, plus 324. Okay. Square root of 324 is 18. See, I can't math sometimes. All right. Okay. See why I don't want to use quadratic formula? X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, 2 times 1. So either x equals negative 16 plus 18 over 2, or x equals negative 16 minus 18 over 2. Negative 16 plus 18 is 2. 2 over 2 is 1. Negative 16 minus 18 is negative 34. Negative 34 over 2 is negative 17. So, same answers no matter which thing you get. Quadratic formula had the largest setup, longest setup, largest numbers, and biggest hiccups. Please solve by factoring when you can. Use completing the square above quadratic formula if it seems best. Okay, number 41. No matter what I do with these problems, it seems most likely that I want to divide everything by negative 2. Number 41, I have negative 2x squared plus 12x equals 36. So this isn't even a method thing. This is divide everything by negative 2 because it's best for the sake of your problem, no matter what. There we go. All right, now you choose your three methods. Now, is it factorable? I don't think it is factorable. I'd have to add the 18 over, but I'm doing that part in my head. That it would have been if the signs of something. Did I write that correct? Yeah, I don't think it's factorable, so I'm going to leave factoring out. I have completing the square or quadratic formula. You know me, completing the square is my go-to as long as I have a 1x squared and even linear coefficient. The negative 18 is already on that side. That's just by nature of the problem. But we're going to be adding the same thing to both sides. That'll be a 9. Yep, not factorable here. This will factor to x minus 3 quantity. This is factorable. x minus 3 quantity squared, and on this side you get negative 9. And let me pause for one moment before I just keep going there. When I say the other thing's not factorable, I mean if I added this 18 over set equal to 0. When you solve by factoring, it must equal 0. Completing the square does not need to have 0 on this side when you factor this side because you're factoring the same thing twice. We can take the square roots here. You cannot take square roots when you're solving by factoring of two non-identical factors. Here you can. Anyway, x minus 3 is plus or minus 3i. Square root of 9 is 3. Square root of negative 9 is 3i. Add 3 over, x is 3 plus or minus 3i. Nothing to approximate or round. Those are the two complex conjugate answers. But we are going to be using quadratic formula to solve this thing as well. Look at the equation on top that I simplified after dividing by negative 2. I will add the negative 8. I will add 18 to both sides. Set it equal to 0. Not factorable, but we will be applying the discriminant as we do b squared minus 4ac. This time I will not be messed up with a minus negative or anything. It's just minus a positive. I get negative 36 as my discriminant, where when I take the square root of it, I'll be getting 6i. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times 1. And 6 and 6 divided by 2 is 3, so 3 plus or minus 3i. Same answers as before. Not too bad. Just not as good. I keep saying that, trying to convince the world. Number 42. Number 42. 2x squared plus 5x equals 4. Immediately I'm telling you square roots out of the picture. Completing the square is not something I'd go to. Only if it's factorable would that be the only other method I'm going to give a shot at. 2x squared plus 5x minus 4 equals 0. Is this factorable? 2 can't go with the 4, so 2 have to go with the 1. Then negative. No, it's not factorable. So your only method, really, the go-to is quadratic formula this time. I will be using quadratic formula. I have no complaints about that. It's the only one that's good here. Discriminant is b squared minus 4ac, which is 25 plus 32, 57. Now, 57, oh, that's not right. 3 times 19. Never mind. I thought you could simplify the radical. You can't. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. 2 times 2 is 4. This is the exact answer set. Did they ask us to round at all? They didn't. Okay, I'm not going to round. I'm going to leave it like that. I was going to say, uh-oh, I didn't round an earlier problem. If I had round, maybe I didn't have to. And then number 43, yeah, that wouldn't do bad. Number 43, I have 3x squared minus 7x plus 13 equals 0. Once again, I'm seeking factorization. I don't think you're going to get it. 13 being a prime number times 30 negative, no. Quadratic formula is really your only go-to. One more time here. Let's do it. You got your discriminant of b squared minus 4ac. Looks to be imaginary anyway. I want to make sure that wasn't imaginary. Yeah, we're good. So this one here is 49 minus 12 times 13. So 156, which is 107, negative 107. 107, I think, is a prime number. So x equals negative b plus or minus the square root. Here's the thing. So the square root of 107, yeah, the square root of negative 107 is I root 107. I root 107 divided by 2a divided by 6. And that's it. If 107 could break down, and I don't see the number that can, it's not 9. Yeah, you can't. It's fine, but there's an I. You pull the I on the outside, the 107 is now positive, and you work with it there. Okay, number 44 to 46. Now, these are no different from the problems you see above. They state it differently, but the very first thing you're going to do is set this thing equal to 0, and then you solve. When they say find the zeros, they say solve for x when y is 0. That's it. So what are we going to do? Set x squared plus 81 equal to 0. Solve using any method. This doesn't change how I'm approaching these problems, right? I'm doing this just like I did the previous ones. Looks like the square root method is well back into play. X squared equals negative 81. Take the square root of both sides, and you get x equals plus or minus 9i. I don't know who's doing quadratic formula here, but I am, just not first. Quadratic formula, your discriminant is b squared minus 4ac. Yeah. Equals 0 minus 324, which is negative 324. I think we saw before 324 is 18 squared. So when you do a quadratic formula, negative b is negative 0, plus or minus, square root of this is 18i. Yeah, all divided by 2 times 1, so plus or minus 9i. Once again, even when I'm doing quadratic formula there, which it is still to me significantly longer than that, I'm still cutting corners by knowing what I'm taking the square root of to get that. All right, number 45, which means I'm making quadratic formula shorter than you probably would be doing there, which means don't use it. The square root method I wasn't using any shorter than anybody else would be. F of x equals x squared minus 2x plus 9. Let's set x squared minus 2x plus 9 equal to 0 and solve. I have my methods. It's not factorable, so I'm going to be using completing the squared and quadratic formula. Let's go with x squared minus 2x plus some blank is negative 9 plus that blank. We've seen this before. This is a 1. This factors to x minus 1 quantity squared, and negative 9 plus 1 is negative 8. We will take the square root of both sides, and we get x minus 1 is, now here's, okay, 8, square root of 8 is root 4 times root 2, or 2 root 2. 2 root 2, but with the negative, there is an I that comes out, so plus or minus 2I root 2. Add the 1, you get 1 plus or minus 2I root 2. And you might say, oh, that was hard. I don't know. But let's go with quadratic formula. Discriminant, right here, b squared minus 4ac is 4 minus 36, or negative 32. Now, maybe we should work this one off. Well, I'm not going to write it off on the side. I'm just going to write the square root of there inside of there so we don't lose any track of what we have. In fact, let's do this. Negative b, I haven't done this in a while. Negative b plus or minus the square root of b squared minus 4ac all over 2a. See, someone might be more inclined to write that first, and I don't doubt it. That's fine. Opposite of negative 2 is positive 2. Square root of 32 is root 16 times root 2, or 4 root 2, but because it is square root of negative 32 before I root 2 over 2. And now all these divide by 2. 2 over 2 and 4 over 2 and the 2 over 2 there. So x is 1 plus or minus 2I root 2. All done. Yeah, I'd still say that was more difficult than completing the square. Larger numbers to simplify. And then number 46. And then a word problem, which I have no idea what will happen there. Number 46. F of x equals negative 8x squared plus 4x minus 1. Let's set this guy equal to 0. I am also going to divide everything by negative 1. I'm not dealing with it. Not factorable. Wait. Maybe it is. It's not a perfect square trinomial. Maybe it's factorable. Oh, that's a minus. Wait. Not factorable. Never mind. Okay. Okay. Quadratic formula. I wish there were some more factorable problems. All right, discriminant b squared minus 4ac is 16 minus 32, or negative 16. Okay. Square root of negative 16 is 4i, yeah? So x equals negative b plus or minus square root of b squared minus 4ac all over 2a. This time your a is 8, so 2 times a is 16. These can all divide by 4 to reduce. You get 1 plus or minus I all over 4. 1i all over 4. That's 46. Okay, number 47 word problem. While marching, a drum major tosses a baton into the air from an initial height of 6 feet. Let's write this. The baton has an initial vertical velocity of 32 feet per second. Does the baton reach a height of 25 feet? 20 feet. Explain your reasoning. So I'm going to make an equation out of this, some h of t. H of t equals, we're going to have gravity take hold. This quadratic term is the gravity part. Initial velocity is upward. That's the 32t. And an initial height of 6 feet is the plus 6. Here's something where at any time t seconds, I will have the height h in feet for this baton. The question is, does the baton reach 25 feet? Does it reach 20 feet? We are going to set, for 20 feet, I'll do it in blue, or 25, I'll do it in blue. We're going to set this equal to 25. We need to see if this has t values that do that. There should be a t here. We need to see if this has t values that do that. My goal isn't to solve for t. My goal is to see if there are solutions for t. So my check is by using the discriminant and see if I get a positive discriminant or 0 when I subtract 25 over. So negative 16t squared plus 32t minus 19 equals 0. I'm going to go ahead and keep that the 16 negative. I'm not solving. I'm just doing discriminant stuff. So discriminant is b squared minus 4ac. I don't love 3 sets of negatives, but I do know that that's subtraction. 32 squared, is that 1024? Yes. So 1024. Oh, I should have saved the calculator. Minus 64 times 19. Wait, 1, 2, I know. 1, 1. Oh, this is going to be negative. Did I say 1, 1? 1138. Let me see if that's it. 64 times 19. Wow, 1216. Where was I going with that? Oh, I was doing 1280 minus. I was doing 1200 minus 62. Okay, what was it? 1216. 1216, which is, I don't know what that calculates to. Minus 1024. I'm bad at some of these things here. Negative 192. Negative 192. Now, I'm not proceeding further on the problem. The negative discriminant tells me that this quadratic equation doesn't have x-intercepts. The idea, if we use that method number 2 scenario, is that y equals this, y equals that. This graph never intersects at some imaginary 25-foot line. It never crosses. So in a case like this, we say, does it reach 25 feet? No, it does not reach 25 feet because of the negative discriminant. Will it reach 20? I'm guessing it will. My guess always is it won't reach the big one and it'll reach the smaller guy. So does it reach 20 feet? Negative 16t squared plus 32t plus 6 equals 20. So now we get negative 16t squared plus 32t. Subtract the 20 over and you get negative 14. And this changes a lot in the discriminant, not the b squared part. But it changes c, and that's enough. Minus 4ac. I don't know if the answer is going to be good. It should be, I'm guessing. So that's 1024 minus, let's do this one right this time. 64 times 14. 64 times 14 is 896. Oh, yeah. 896. Which is 2. Ugh. I don't want to get it wrong. 128. It's positive. It's positive. It does reach 20 feet. Somewhere between 20 and 25 feet, it no longer reaches. It peaks out somewhere. So that's a second way we could do this problem that I never just did. And I totally could have. But it's, well, we're not in any one method of problem. So let me give you another version of what we could have done. we could have found the vertex. We could have written it in vertex form and figured out what that max height y value was. So we could have gone all the way with that h of t, the initial one, h of t equals negative 16t squared, because these numbers are nice, plus 32t, that's probably what I should have done in the first place, plus 6. The problems aren't always this good, though. Negative 16. I'm going to factor that out of the t squared and the 32t and all that. So I'll get minus 2t here. Now the 6 will not be involved in this completing the square thing. When I add this, whatever I subtract here will multiply by negative 16. Okay. So that's a 1, and that's a 1. So h of t in vertex form will be negative 16 times t minus 1 squared, and then 6 plus 16 is 22, plus 22. The vertex is at 1 comma 22. That means 1 second. After 1 second, it has a max height of 22 feet. What does that tell you? It tells you it will reach 20 feet and it will not reach 25 feet, right? So that's another way you can go about it using the vertex stuff. That's an alternative method to that. And it was actually faster than doing both of those. I didn't have to use a calculator. So it depends on what you have and what you're dealing with. That's the using any method kind of thing. Okay, let's go to 4.8, and after that we have 4.9, which I haven't covered. I haven't made a video for it yet when I started recording this, so we'll see where I'm at with it. 4.8, solving nonlinear systems of equations. So we have solving by substitution for this one example here. You have a system of equations, two equations, y equals this and y equals that. What I'd like to do is set these two equal to each other. Basically have this expression plug in for the y in the other equation. Because they're both the equations of the system, they both represent the same y's. If y equals this, this can take y's place. I'll have an equation that says negative x plus 1 equals x squared minus 5. In essence, an equation with all x's in it. I can solve for x, or the x's. In this case, set it equal to 0 and solve by factoring and zero product property. You get x equals negative 3 and 2. Now you're not done, because the solution to a system is what x's give you which y's. If x is negative 3, the y value is 4. If x equals 2, the y value is negative 1, and you can plug it into either equation. The goal of what we were trying to find is if these were graphed, some guy here and some guy here, what are the solutions to the system? What values of x give you the same y's for both equations? So they substitute it into the easier of the two equations. Generally, it's the linear one, and it looks like that's what they did, because you would get the same y out regardless. Plug negative 3 into this equation, you get 4 for y. Plug 2 into this equation, you get negative 1 for y. So they're ordered pairs, negative 3 comma 4 and 2 comma negative 1. And we're about to do this stuff on the next 3 problems. Number 48, we have y equals x squared minus 2x minus 4. Now they say solve using any method. I'm unlikely to be solving by graphing. We did that earlier on. I was going to say, in fact, I wonder if this is the same problem as earlier. It's not. It almost reminded me of it. Y equals negative 5. Let's use the substitution as you just kind of saw before. I can set these two things equal to each other. X squared minus 2x minus 4 equals negative 5. I'll find a different problem to do. I don't know. Substitution seems easiest for all of these. I'm going to say that. There's the elimination method, which is subtracting one thing with the one above it or below it. You know what? I'm not a big elimination guy. Add 5 over, you get x squared minus 2x plus 1 equals 0. If I had a nickel for every time I had this equation today, I swear it's the same writer who did the same thing over and over, didn't know how to fix these. This factors to this, x minus 1 squared equals 0. Take the square root of both sides and add 1, x equals 1. There's only one solution to this. I'm not done, but there's only one solution to this thing where x equals 1. Now you could substitute 1 into either equation, but if you notice, I already have an equation that says y equals negative 5. There's only one place where these guys intersect. Given that the y equals negative 5 with this thing, your ordered pair is 1 comma negative 5, and that's it, and that's all. So kind of a weirder, easier version of any other problem you'd have. That's number 48. Number 49, you have y equals x squared minus 9 and y equals 2x plus 5. For the sake of variety, I'm going to use the elimination method this time. But for the elimination method, you're basically subtracting down these lists, but you want to line some things up like so. We want to make sure that things are in line. So I'm going to subtract everything. I'm going to change all these signs. I don't always write it like that, but for the sake of this problem, I will. Subtract everything to eliminate the y's and only have x's left. Y minus y is 0. X squared comes down. Subtracting the 2x here, and negative 9 minus 5 is negative 14. So you have this equation, which does not appear to be factorable. So now I just want to make sure I did it right. I did. Non-factorable, so we're going to solve using a method of choice. I'll go ahead and use completing the square. I'm not doing more than one method this time. I'm going to add the 14 over to do completing the square here. So this will be a 1. Oh my gosh. So this will be a 1 and a 1. This factors to x minus 1 squared. I see this way too often. Equals 15, and solve using square roots. And we get x minus 1 equals plus or minus root 15. So x equals 1 plus or minus root 15. But you have to once again remember that this is not the only solution set that's available. Excuse me. These are not the only. That's not all you do to finish. You have to find y in this scenario. Now, I'd be caught dead substituting 1 plus or minus root 15 into the quadratic. Then you'd have to square and expand that, and that takes a little bit to do. I'm definitely still going to use this bottom one here to find them. There's 1 plus root 15 and 1 minus root 15. So when you do 2 times 1 plus root 15 and then the plus 5, you get 2 plus 2 root 15 plus 5, or 7 plus 2 root 15. There's one set when you plug in 1 plus root 15. When you plug in 1 minus root 15, you get 2 times 1 minus root 15 plus 5. Honestly, dot to dot, you're going to get down to the same thing, only now it'll be 7 minus 2 root 15. So your two answers as ordered pairs with exact numbers. You get an x of 1 plus root 15 comma 7 plus 2 root 15. And for the other one, you get 1 minus root 15 comma 7 minus 2 root 15. There are your two sets. I don't know. Those are kind of weird. Definitely don't want to solve that one by graphing. Unless you're approximating, which number 50 looks like it's something we're going to maybe have to do, because we can't give an algebraic approach to this. I would be fine, honestly, I would be fine graphing this on my own if I knew they would hit integer solutions, and I don't know that they do at all. I have no idea. And I'm not going to graph that bottom one. And we haven't practiced graphing the top one with a vertical shift. So there's no way I can do that in that form. I will be using substitution in the manner here where I set one equal to the other. I get 2 times 1/2 x. By the way, these do not multiply together. Order of operations. But I'm going to be basically using a method number 1 case of setting everything on one side of the equation in standard form, plus x squared plus x. Subtract the 4 over with that 5, it's negative 9. Set it equal to 0. I'm going to graph this and find its x-intercept, or intercept and round to the nearest 3 decimal places, because they don't tell us what to round to. So I'm going to go and pop up whatchamacallit. Oh, you know what? You never saw me draw anything over here. I forgot. Sometimes I'm missing stuff. You never saw me draw this little guy. Anyway. Sorry about that. I hope there weren't a lot of times where I did something like that. Okay, I'm going to pop up the graphing calculator. So we're going to do 2 times 1/2 to the x power plus x squared minus plus x minus 9. Now the graph of this thing looks like that. It crosses twice. So I'm going to go ahead and find those 2 points of intersection by using the 0 feature. So I got one of negative 1.878 about. I'm not going to do anything else from these negative 878. And let's figure out that other one. Hope your teacher teaches you how to use these things to kind of graph with later. 2.482, about 2.482. Okay. So those were those ones, not doing much on the graphing bit, but when it comes to solved with graphing calc. And I think that's kind of what they're expecting you to do. I mean, they might ask you to use a table and plug in numbers until it works, or approximate by plugging in different numbers. We're not really quite doing any of that. Okay, last section is 4.9. Now, I personally have not done any of the video stuff with this, so let's see to what extent they do problems of certain types. Graph the system. Oh, we do have to graph them. Graph the system of quadratic inequalities. So, when it comes to graphing inequality, well, when it comes to graphing in general, we're going to draw a boundary curve or a boundary line, basically graph it as if it's y equals. We're going to use a dotted line like they do here if you don't include points on the line or curves when it's a greater than or less than, but not the or equal to's. So y is greater than x squared minus 2 is the one that's in red. And the one that's in blue is negative x squared minus 3x plus 4. Solid line. The shading has to do with your solutions here. Greater than, you shade above the curve, or within in this case, and you shade below the curve, or I guess within in this case when it's less than. And the overlapping shaded region, the thing inside here that almost looks purplish, the intersection of red and blue, are the solutions to the system of inequalities. Now the purple, oh, they call it purple as well. So anything inside here, including 0, 0, things like that, this is a solution to the system. If I plug in 0, 0, or negative 2, 4, things like that to both inequalities, I would get true statements out for both. There's a very small set that work, but those do. Now, on numbers 51 to 53, we're just graphing individual inequalities. So in number 51, we have y is greater than x squared plus 8x plus 16. I think we've seen this exact graph before, so I don't have much need to kind of go beyond. I'll graph it again, but I'm going to point to where it was. It was y equals x squared, da da da. Look how much we've done so far, guys. We've accomplished so much today. It was right here, x squared plus 8x plus 16. It factors to x plus 4 quantity squared. We're going to see this graph once again. However, given the nature of what we have to do either dotted or solid lines and a shaded region when we do the graphs. So let's see where we're going to go with that. So I'm going to change it into y is greater than x plus 4 quantity squared. Yes, if you know vertex form, you can get into that and use that vertex form. I'm going to use the smaller graph thing, though. I think last time I used the bigger graph because I did like that method number 2 stuff. So here, x plus 4 quantity squared, but it's y is greater than, etc. So let's first graph this boundary curve like that. Now, as far as the curve goes, greater than, not greater than, or equal to, we will be using a dotted line to or a dotted curve to represent this. Points on the curve are not solutions to the inequality, only when y's are greater than points on the curve. That means points above them at any given x value. So we will be shading above, and pardon my means of shading here. I'm going to do it like that. Not quite like that. I'm going to do it like that. There we go. I think that'll kind of work out and carry over. Whoa, that's fine. All right, there's my shading for that first guy. All right, that is number 51. Number 52. Kind of thinking about which way I want to do this when it comes to teaching it. Y is greater than or equal to x squared plus 6x plus 8. My focus really shouldn't be on the graphing portions, but I can use intercept form. Now, as far as intercept form, I'm going to think of, and I'm changing this to equals for a moment because it's really all about critical points right now. I'm going to factor this into x plus 4 times x plus 2. Your x-intercepts in that case would be negative 4 and negative 2. My goal right now is to kind of figure out what the graph looks like first and foremost. The second part is to talk about the shading and dotted and solid lines and things like that. So right now I'm getting more in the, sorry, I'm trying to get this small graph here. There we go. My goal right now is to I'm figuring out x-intercepts by using factored form, setting this thing equal to 0. So negative 4 and negative 2, like that. The axis of symmetry is right in between. AOS is y equals -3. And then your y value for that, x equals -3. And then your y value for that, plug -3 in. -3 plus 4 is 1. -3 plus 2 is -1. So that's -1. So you have a vertex like that. So 1, 1, 2, 4, 3, 9. And the 9 value, the y-intercept is 8. So 9 up also, you get 8 right there. That works. This is greater than or equal to, which means shading above, but also shading above a solid line. Points on the line also qualify here. Now, I didn't seem to use -b over 2a this time to get my points because I wanted to use another form. Heck, I could have used completing the square. I had a lot of different ways, but very rarely are these ones factorable. Actually, I don't know if that's going to be true for these cases. I might get a lot that are factorable here. But since I did have one, I wanted to use factored form at least once. It's been a minute. I think I balked at the chance to use it earlier, so now I wanted to. That's going to be good enough. As I try and make it better. That's actually pretty good. All right, number 53. See, no matter what I choose here, even factored form, even if it's factorable, which actually might be, no matter what I choose here is not going to be a winner. X squared plus y is less than or equal to 7x minus 12. I'm going to subtract the x squared over and to get -x squared plus 7x minus 12. I'm going to use the -b over 2a concept this time. Yeah, happy we get to use one of those. Haven't seen that one in quite a while. The vertex x value is -b over 2a, which is -7 over -2, or 7 halves. That's 3.5. X equals 3.5. The y value, you have -7 halves squared plus 7 times 7 halves minus 12. 7 halves squared is 49 fourths, so we get -49 fourths, and then you'll do plus 49 halves, which is positive 49 fourths, minus 12 is 48 fourths. 49 fourths minus 48 fourths is 1/4. So your vertex is at 7 halves, comma, 1/4. So 3.5 over, I'm just a quarter up like that. However, this graph has a -1 stretch factor. So over 1 down 1, like so. Over 2 down 4. And over 3 down 9. That's too far over. Is less than or equal to. Now, for once, I'd like to do one that's outside of these parabolas. This is still on the inside of the parabola. Now that it goes less than, it goes under. And when it faces downward, it'll stay within. That's not always the case. I wonder if they're going to make it always the case, because maybe it gets hard to color if you don't. But this thing here will look like this guy, shaded on the inside. I tried. It's kind of hard with this tool when this happens, but that's okay. All right, so there's the shading of number 53. I got 4 more problems to go. I hope I have enough room on the old computer here with 2 hours done. I should have. Number 54, graph the system of quadratic inequalities. This one probably gives me an option to do some completing the square, stuff like that. But graphing the system, you're just graphing 2 and 1 now. So I have x squared minus 4x plus 8 is greater than y. And -x squared plus 4x plus 2 is less than or equal to y. First things first, guys, write the y on the other side of these things, but make sure you flip the inequality with it. You got to know whether you're graphing above or below. Compare the y to your values. Don't do it the other way around. So over here, we're going to get y is greater than or equal to -x squared plus 4x plus 2. I think both these are prime for like that completing the square, kind of biz here. So I'll say x squared minus 4x plus 4 plus 8 minus 4. This is for bleu and green. And this will be y is less than x minus 2 quantity squared plus 4. So there's vertex form of the first guy in blue. And in green, we're going to get y is greater than or equal to, factor a negative 1 out. I'm going to give myself a little more room, actually. I'll graph on the right side. Y is greater than or equal to, factor the negative out. You get x squared minus 4x plus blank. Plus 2 minus the opposite of said blank. That'll be a 4. We just saw that from the previous one. So this will be y is greater than or equal to negative x minus 2 quantity squared plus 2 plus 4, which is plus 6. So we're going to be graphing both of these guys here. So let's see what those look like. As long as I can see them in the shot. All right. In blue, I have a vertex of 2, 4. 2, 4. I got a stretch of 1, 1, 2, 4, and that's all I can fit. Less than, okay, now less than will mean dotted line, but it will also mean shading underneath. So I get an opportunity to actually do that. Now that it's a system, it'll be quite a handful. Less than is anything underneath that, so it's going to be, wow, quite a bit. This time I get to kind of embolden this thing. I'm going to go big, boom. Everything here is its own big old shaded region. So the overlapping shaded region works itself out in quite a way. Unless I mess something up there, that looks exactly like it's going to have to. Okay. Definitely ruining my pen while doing that. Okay, that'll be good enough there. Now in green, probably should have shaded after the fact, or I'm going to show the overlapping shaded region. But in green, x minus 2 plus 6. So right here, and now it's going to be going downward. So this guy will be going this way. 2, 4, 3, 9. And 4, 16 is all the way at the bottom. So this one's a solid line, as it's a greater than or equal to. Okay, this will be another interesting overlapping or shaded region part. So solid line, and we're going to shade above this guy. So now for the first time, we got to do it for both of these things. It's just going to look a little wonky is all. So we got, might be a pukey color as well. So here in green, this is all above that green here. And you might be confused as to how that represents aboveness. That's because this graph goes down forever. It goes left forever. It goes down forever. It goes right forever. So somewhere down there, you'd find parts of the curve, and you'd see that green shaded region existing. So it doesn't just end here. This window goes on forever. We just don't happen to see that. So the overlapping shaded region is everything that's in both blue and green together at the same time. Not just this blue, not just this green, and definitely not that white. But sketching that overlapping shaded region thing would look just like that. That is number 54. 3 more problems. Number 55, and they're really going to test our graphing abilities for all these ones, aren't they? Number 55, we have 2x squared minus x is greater than or equal to y minus 5. I hate them for this problem this late in the game. And then we have 0.5 x squared is greater than y minus 2x minus 1. So same biz as before, guys. I'm going to be getting y by itself on both of these here, but I'm also going to put it on the other side of the inequality in a bit. So 2x squared minus x plus 5 is greater than or equal to y, or y is less than or equal to 2x squared minus x plus 5 is one inequality on this thing. The other one is going to be adding the 2x, adding the 1 over, you get 0.5x squared plus 2x plus 1 is greater than y, or y is less than 0.5x squared. I'm going to write that as 1/2, y'all. 1/2 x squared, probably the only person who likes fractions more than this, plus 2x plus 1. Okay, so we got to graph both of these. I like this one a lot more than I like that one here. We're going to use negative b over 2a for both of these, if you don't mind. So vertex here, the x value of this guy is negative b over 2a, which is 1/4. The y value is 2 times 1/4 squared minus 1/4 plus 5, or 1/4 squared is 1/16 times 2 is 1/8. So 1/8 minus 1/4, which is negative 1/8, plus 5. 5 is 40/8, so negative 1/8 plus 40, hold on, times 8 over 8, plus 40/8 is 39/8. So we have a vertex there of 1/4, 39/8. Now 39/8 is 4 and 7/8. 4 and 7/8. So when it comes to that portion of the graph, I'll get to green afterward. But we got that. Okay. So let's get this blue. We got 1/4. Oh gosh. 1/4, 4 and 7/8. 4 and 7/8, kind of like up there. Stretch factor is 2. I'm only going to be able to fit like a over 1 up 2 kind of thing. Over 1 up 2 and over 1 up 2. Like that. Then it just stretches upward. So not beautiful. This should kind of confirm that this has a y-intercept of 5. You can see that I'm kind of hitting 5 right there. So that's kind of nice where that works out. And this is less than or equal to. So once again, they're doing this thing to me where I'm going to be shading underneath this whole guy right here. So the less than or equal to shading underneath. So I wished for it for just one problem, not for every problem, that barely touches part of the graph. And then the rest of it does this. You can tell I'm very opinionated about this stuff. So here we go. Touch everything but just the little part that's hooked inside. Yet it looks like I did it anyway. Yep. And that happened. Okay. Green. Green should be, well, I don't know how the Y value is going to be. I think the Y value should be fine, but green should be a lot better. So for the vertex, you got x equals negative b over 2a. 2 times 1/2 is 1, so you get negative 2. The y value, yeah, you get 1/2 times negative 2 squared plus 2 times negative 2 plus 1. Whoops, y equals. Negative 2 squared is 4, divided by 2 is 2. 2 minus 4 is negative 2, plus 1 is negative 1. So your vertex here is at negative 2, negative 1. Much better. And this is just a 1/2 stretch factor. Y will be less than. So negative 2, negative 1. 1/2 stretch factor over 1 up 1/2 over 2 up half of 4, which is 2. Over 3 up half of 9, which is 4.5. Over 4 up half of 16, which is 8. And over 5 up half of 5 is 12.5. It's kind of higher up there, which we can't exactly reach. This will be a dotted line or curve because reasons. Because it's strictly less than, not less than or equal to. You can see how it kind of sits on the outside of this thing, which is interesting. But we will be shading underneath this one as well. Now, the overlapping shaded region is where both of them are shaded. These are interesting problems, just the way that they made these ones. Normally, they'd have, like, interesting ways to go about having their look. And, I mean, good, decent ways. Like, the one that they gave in the example, that one looks good and fine as far as, like, what's normal. Now they're doing all this stuff, and it's quite odd. I don't know how to explain it other than it's quite odd. But the overlapping shaded region is basically what's within here. Basically everything that's just less than that green one, really. The blue doesn't even really qualify in its own right. Everything that's green is also blue. And there's that. All right, number 56. They just made things significantly worse. At least for the first inequality. Second one, yeah, pretty much. All right, number 56. Can we at least shade inside of a parabola this time? Let's see. Negative 3x squared minus 2x is less than or equal to y plus 1. And negative 2x squared plus x minus 5 is greater than negative y. Okay, for the... First of all, that bottom one looks 55, 2x. Okay, let's see if we get this thing back, something like that, or at least this, I'm going to use that, just so you know. I'm just going to copy and paste it if we just did the graph. So we'll see if that happens. If I divide everything by negative, well, here, if I switch everything, negative y is now less than negative 2x squared plus x minus 5. But if I divide everything by negative 1, then the inequality flips to a greater than there. So minus x plus 5. Is that the same thing? Yes, it is. I'm just going to copy and paste that over. The greater than will be the different part, though. So I will be copying that over here in blue. Sorry, but that's what I'm just going to be doing. That's for the bottom one. The green one, we got to subtract 1 over. So we got negative 3x squared minus 2x minus 1 is less than or equal to y. And then I'll put the y on the other side. Y is greater than or equal to negative 3x squared minus 2x minus 1. Now this one's going to be kind of rough. So the vertex being at negative b over 2a. Does this factor? No, they'd be all pluses. No. All right, vertex at negative b over 2a, which is 2 over negative 6, or negative 1/3. Jerks. So negative 1/3. The y value for that is negative 3 times negative 1/3 squared minus 2 times negative 1/3 minus 1. Okay. Negative 3 times, negative 1/3 squared is 1/9. Negative 3 times that is negative 1/3. This is plus 2/3, which is positive 1/3, minus 1, which is negative 2/3. So you get negative 1/3 comma negative 2/3 is your vertex here. And we're going to graph that and use a vertical stretch factor of negative 3. It's going to go downward. So let's do this. I already have the graph for that other one. Let's just kind of copy and paste it in. Oh, it's greater than. Okay, I'll just still use it. So it's. Oh, yeah, I kind of want to copy and paste it in. How do I do that? Give me one moment here. I got to figure out how to get this thing, like, right. Okay, you know what? Maybe I can't. Maybe I can't. No, yeah, I can. Let me copy and paste the whole thing and erase what I don't want. Sorry about this. I'm going to be kind of lazy at the end. I really, really, really just want that graph. I don't want to plot. I don't want to plot any more points that I don't have to. Okay. There we go. Okay. So I'm going to make it dotted, though, instead. We're going to shade above and make it dotted. So by dotted, dot, 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 like that. Just erase bits. There we go. Keep the last one how it was. Shading above that first one. So you got to graph it the same if you're following along. Shading above that first one is just like that. Okay. There we go. I don't know why I just didn't see that normally. And now this other one's still kind of hectic-y, but negative 1/3, comma, negative 2/3, like that. But in green. Okay, so down, over 1, down 3. It would be over 2, down 12. Really can't fit that. I just know it's going to be pretty sharp down there. Probably right around where that line would go. Y is strictly greater than, excuse me, y is greater than or equal to on this one, so I will be going above. Kind of weird. But let's deal with it. Yeah, so greater than or equal to be shading above. I really don't want to feel like I made any mistakes here. I got negative 1 boom thing there and everything. Oh, I think it's good. I just, because the graphs are not really, normally they make these kind of look like you'd know what you're doing with your answer just because it should look kind of right. This just looks like randomness. I think that's what I'm saying. They're not kind of finding ones like, their example is a really good one that looked like it had structure to it. This one, not quite, but shading above. And remember, when I shade above, I totally ignore what I'm doing when it comes to that blue and stuff. Yeah, that's part of the answer. But I'm ignoring the concept of like, oh my gosh, I have to keep that in mind when I shade. No. You just shade as you shade. The overlapping shaded region is everything inside green and blue together. Okay, and that is number 56. Last problem. Number 57, we are solving these two things here. It's two different questions. I believe. So 57A, let's see, 2 hours, 14 minutes. We're still good. Didn't run out of time yet. It's 57A. We're solving 3x squared plus 2 is less than or equal to 5x. Now, I haven't covered these yet. I've done them in my lifetime, but I don't know how the book will go about it. I imagine they'll do the same thing, which is this. I don't know how they're going to specifically talk about parts, though. That's the problem with me doing this after the fact, or before the fact. But what we're going to do is solve this thing as if it equaled 0. So I'm going to begin with that. 3x squared minus 5x plus 2 equals 0. I'll explain why in a moment. This looks factorable. Yes, it's factorable. This looks factorable. All right. Here we're going to get add 2 divided by 3, x equals 2/3, and here we're going to get x equals 1. Now, these aren't answers, but these are what are known as critical points, CP. These are critical points. These are points where if we graphed, my goal is not to graph this, but if we graphed this crosses at x equals 1 and x equals 2/3, and it's an upward facing graph. It does something like this, just a parabola, boom, boom. We want to find out what parts of this parabola are underneath the x-axis. Remember when we graphed when we solved when they equaled 0 by graphing? We found out where they crossed the x-axis, which would be here and here. I want to find out where it's underneath, which is a very tiny region. Now that's without knowing the graph itself. You may know the graph, and this is where these things called sign charts come into play. What a sign chart is you test points by substituting them in, and you see what kinds of signs you get from the scenario, and you try to see when the left side is less than 0, when you get positive versus negative. So with these being critical points here's our critical points table. I'm going to put 2/3 on it. I'm going to put 1 on it. To the left of 2/3, between 2/3 and 1, and to the right of 1 are where the graph does 3 distinct things. Where it can change signs, and you can see by this parabola where that's exactly happening. To the left of 2/3, it looks like you should get positive numbers, like if I plugged in 0. If I plugged in 0, I get 3 times 0 squared, which is 0, minus 5 times 0, which is 0, plus 2. And 2 is greater than 0. So you get a positive number out from that. Okay. Now, here, to the right of 1, if I plug in like 10, 3 times 10 squared is 300. Minus, hold on a second, did I say that right? Yeah, when I plug in 10, 3 times 10 squared is 300 minus 50, which is 250, plus 2 is 250. It's a positive number. Now when I plug in something between 2/3 and 1, that's really hard to do, but we'll try it. Let's try 4/5. Now, by the way, you don't have to use these squared and stuff. I can use this as well. 3 times 4/5 is 12/5. 12/5 minus 2 is 10/5. That you get 2/5, a positive number. Times 4/5 minus 1 is negative 1/5. Negative 1/5 times 2/5 is negative 2/25. That's a negative number. Point is, it's really small. It's always going to be a fraction. It's kind of crazy. This sign chart helps us dictate when we change from positive, because remember, these are zeros right here. When we go from positive to negative, when is this less than or equal to 0? It's equal to 0 at 2/3. It's equal to 0 at 1. It's less than 0 between 2/3 and 1. Sorry, this looks like a face, and I'm looking at it like, hungry. Okay, so between 2/3 and 1, this graph is negative. It's underneath the x-axis. That's what we're looking at. So as far as the answer, the solutions to the x values, where this left side is less than or equal to the right side, where this gets you negative or 0, is x is between 2/3 and 1, and it includes both of them. Between 2/3 and 1 on x is when you get negative values out from this set. Part B, let's do it again, and let's see if this is easier, harder, the same, whatever. Negative x squared minus 10x is less than 21. Now, who knows? Maybe when I actually hit the section, I can explain it a lot better based on the examples that they use. Or I can explain it in the way that the book uses it and stay consistent. I'm going to add these over, which means 0 is still on that side. It's important for me to be careful in what I'm doing. Now I'm going to flip it all over and set it greater than 0 like that. This is definitely factorable with 7 and 3. Excuse me, I'm going to see how this works when it equals 0, right? That's kind of my thing here first. Set it equal to 0, factor and solve. Zero product property states that x is equal to -7 or x equals -3. Now, once again, if you have the idea of the graph, then that would totally work out in your favor. As in, I'm doing it for this one, this positive x graph here. The nature of this graph is at -7 and -3, we cross the x-axis. We cross the x-axis, and this graph once again goes down and comes back up. It's assumed that we'll be negative between -7 and 3, and we'll be positive to the left of -7 and to the right of 3, which is really what we're looking for when the points are positive. Not when they're 0, not when they're negative. So I'm expecting a very specific kind of solution set here. But if I use a sign chart, once again, I have -7 and -3. What happens to the left of -7, to the right of -3, and in between? To the left of -7, let's plug in like -10. I'm going to use the factored form version as if it's y equals. -10, and I don't care about the number, I care about sign. -10 plus 7 is negative. -10 plus 3 is negative. Negative times a negative is a positive. Let's plug in something like -5. -5 plus 7 is positive. -5 plus 3 is negative. Positive times negative is negative. Remember, these are zeros. Let's plug in 0. 0 plus 7, 0 plus 3. That's positive. So you can see we're positive to the left of -7, positive to the right of -3. So the solution set will be x is less than -7. That'll give you positive numbers. Or x is greater than -3. They might use other forms of these things. They might unionize them. They might use, instead of or, they might have this symbol right there, which stands for union. It's a way of joining things that are not in between two bits, and that's what that would look like. I think I kind of got this taken care of the way that I'm looking for, but it would be in this range and in this range here. Okay, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Lord knows that I could use the rest right now. Thanks for watching, and I'm going to try and fill in some of the gaps if I didn't get some videos in within some time. Otherwise, you're not going to see some Chapter 5, at least for a few weeks here, probably. It's going to be a bit because it's all we're covering this semester. All right, guys, take care. I will see you in the next one.